Hello, and welcome to the 9th webinar in our Lunch, Learn, and Dance Wellness webinar series, EMF and Wi-Fi. I am Lynn McDonald, Liaison Scientist with the Radiation Safety Institute of Canada. Joining me in our chat room is Maria Costa and our Manager of Training, Tara Hargraves. We also have Natalia Mosiani, our CEO. Kim Ramos from Arawaku Latin Dance Company in Toronto will lead us in dance beginning at 12:30. Let's take a moment to go over the functionality of the Zoom webinar. The audio and video will be from the presenters only. We have found that although you can access the audio through the computer or telephone, the quality of sound tends to be better when listening from a computer. There is a chat feature where people can discuss. If you would like, take a moment now to say hello and where you are from. If you have questions arriving from the content, please enter them under the Q&A section. As the webinar is only a half hour in length and it's immediately followed by our dance session, any questions not answered during this session by Tara will be answered afterwards and posted on the website on the webinar section. This can be found under Education Webinars. I will be sending a confirmation of attendance email after the webinar and will include a link to the page with that communication. I will also include the topics covered and the length of time spent in the webinar, as some people have requested this to send to their professional association. Lastly, I have automatic closed captioning enabled in the slide presentation. If they are being blocked by your Zoom controls, you should be able to select a different way to view the webinar in Zoom, which make them easier to see. In this session, we will build an understanding of EMF by first looking at electricity, magnetism, and electromagnetic radiation. We will then look at organizations which research and develop guidelines for the use of EMF. Lastly, we will look at sources, health effects, and exposure guidelines for static electric, static magnetic, low frequency EMF, and radio frequency EMF, which includes Wi-Fi. Electromagnetism is a vast topic which has applications in physics, chemistry, biology, engineering, etc. The webinar is an overview, so scientific details are focused on what is needed for the basic understanding of EMF and Wi-Fi. Information and images regarding research and regulation come directly from the respective organization's materials. To understand electromagnetic fields, or EMF, we must know a bit about electricity, magnetism, and the relationship between them. Electricity is a characteristic of matter, just as mass is. An electric charge, for example, an electron, proton, or ion, produces an electric field in space. Depending upon the shape of the charged object, the fields have different shapes. When looking at field diagrams, such as those shown here, the field is strongest where the lines are closest. If you put a charged object in an electric field, it will feel a force. The arrows in a field diagram point to which way a positive charge would feel a force if put in the field. The unit for electric field intensity is a volt per meter. A flow of electrons is called an electric current. The unit electric current is the ampere. The electric field in a long, straight, current-carrying wire is strong near the wire and then falls off as a linear function of the distance from the wire. Of course, we do not tend to keep our wires perfectly straight, and they're not infinitely long, so the electric field pattern will be somewhat different for real-life situations. But in most cases, electric fields tend to be stronger near a charged object and fall off away from the object. Some configurations will cause the field strength to fall off faster than others. Magnetism is another characteristic of matter. Certain materials called magnets produce magnetic fields in space. Unlike with charge, where you can have isolated positive or negative charge, you cannot have a north pole without having a south pole. Magnetic fields are also produced by electric current or changing electric fields. The magnetic field produced by a current is perpendicular to the direction that the current is flowing. The symbol for magnetic flux density, which is an indication of field strength, is B. The unit of magnetic flux density is the Gauss or Tesla, depending upon the measurement system. The magnetic field in a long, straight, current-carrying wire runs perpendicular to the electric field as shown. Similar to the electric field strength, in most cases, magnetic fields tend to be stronger near the source and fall off as you move away, and some configurations will cause the field strength to fall off faster than others. When electric or magnetic fields are not changing with time, we call them static. Once thought to be separate forces, as scientists gained an understanding of electric and magnetic forces, it was determined that they were both aspects of one force called the electromagnetic force. Electricity and magnetism, which arise from these forces, are part of the same phenomena, electromagnetism. Combined electric and magnetic fields can be considered together as electromagnetic fields, or EMF. Electromagnetic radiation is the transfer of energy out from a source in the form of electromagnetic waves or streams of massless and chargeless particles called photons. An electromagnetic wave is the propagation of time-varying electric and magnetic fields in space. In space and in most materials, the fields oscillate at right angles and in phase to each other, as shown in the animation. The properties of an electromagnetic wave, including what materials will reflect or transmit it, are determined by its frequency, wavelength, and photon energy, which are all interrelated. Wavelength is a measure of the distance between two repeating points, such as a crest of a wave. Frequency is how many waves occur in a period of time. As wavelength increases, frequency and photon energy decreases. Wavelength is measured in meters. The unit of frequency is the hertz. The unit for photon energy is the electron volt. Metric prefixes are often used when discussing the electromagnetic spectrum, as its ranges are very broad. Note that changing the wavelength and frequency of the wave does not change its amplitude or height. In terms of visible light, different frequencies, wavelengths, or photon energies relate to different colors. Changing the amplitude or height of the wave, on the other hand, would change the number of photons being emitted or detected, which your eye would interpret as the light being more bright or dim. Although we cannot see any EMF radiation except visible light, these understandings can be useful when discussing invisible EMF as well. While the electromagnetic radiation spectrum runs from very low frequency radio waves through to high frequency gamma rays, for today's webinar, we're going to discuss static fields and radio frequency section of the electromagnetic spectrum. But first, let's look at agencies involved in non-ionizing radiation protection and standards, as all the frequencies we discussed today are non-ionizing. As we were just discussing electromagnetic frequency, it makes sense to first mention the International Telecommunications Union, or ITU. It is the United Nations specialized agency for information and communication technologies. Just as waves in the ocean can interfere with one another, so can electromagnetic waves. To avoid this interference, part of the ITU's role is to allocate bands in the radio frequency spectrum for specific purposes. The RF spectrum is subdivided into bands based on frequency. Different frequencies of electromagnetic radiation behave differently when they interact with matter. The ITU considers these characteristics when determining the usage appropriate to that band. The ITU sponsors regularly held World Radio Communication Conferences, or WRCs, to extend, review, and revise frequency allocations amongst the various uses. Much of the following information on health effects and exposure guidelines comes from the International Commission on Non-Ionizing Radiation Protection, or ICNIRP. The organization is a not-for-profit based in Germany. It is formally recognized as an official collaborating non-state actor by the World Health Organization and the International Labour Organization. The ICNIRP is also consulted by the European Commission. It is linked to many organizations engaged in non-ionizing radiation protection worldwide through diverse collaborative projects. The aim of the ICNIRP is to protect people and the environment against adverse effects of non-ionizing radiation. They develop and disseminate science-based advice on limiting exposure to non-ionizing radiation. ICNIRP experts base their advice on scientific publications about biological effects and action mechanisms of radiation for the whole non-ionizing radiation frequency range. ICNIRP's protection advice is formulated in its guidelines, reviews, and statements, which are publicly and freely available online. To give an understanding of what goes into the preparation of a guideline, we'll use the RF guides as an example. All scientific literature of good scientific quality was used to set the guidelines. This was based on major reviews by the World Health Organization, the Swedish Radiation Safety Authority, the Scientific Committee on Emerging and Newly Identified Health Risks, as well as individual studies identified following these reviews. The literature included research searching for effects of both brief and long-term exposures to radio frequency electromagnetic fields, or RF EMF, on both intermediate, for example, pain, and delayed, for example, cancer, health outcomes. This included evaluation of self-reported hypersensitivity to RF EMF exposure. Importantly, the research that focused on potential adverse health effects of RF EMF exposure did not make any assumptions about the mechanisms of action of the RF EMF, for example, thermal versus non-thermal effects, but merely looked at any verified or substantiated adverse health effect, and where identified, instigated protective measures regardless of mechanism. The ICNIRP and associate organizations continuously work with the global scientific community to better understand the health consequences of exposures to non-ionizing radiation. They put out statements to the scientific community to suggest areas where more research is needed. For example, in their most recent summary, gaps were found to be for specific aspects in the area of pain perception, neurodegenerative disease, childhood leukemia, neural network firing patterns, free radical lifetimes, and dosimetry and modeling. The text of the guidelines more fully explains what is already well understood and in what areas more information is desirable. The International Agency on Research on Cancer is the specialized cancer agency of the World Health Organization. It maintains and publishes information on cancer, including the IARC monographs. The IARC monographs identify environmental factors that are carcinogenic hazards to humans. These include chemicals, complex mixtures, occupational exposures, physical agents, biological agents, and lifestyle factors. National health agencies can use this information as scientific support for their actions to prevent exposures to potential carcinogens. Interdisciplinary working groups of expert scientists review the published studies and assess the strength of the available evidence that an agent can cause cancer in humans. The principles, procedures, and scientific criteria that guide the evaluations are described in the preamble to the IARC monographs. There are 4 groupings of substances within the monographs. Group 1, carcinogenic to humans. Group 2A, probably carcinogenic to humans. Group 2B, possibly carcinogenic to humans. And Group 3, not classifiable. Since 1971, more than 1,000 agents have been evaluated, of which more than 500 have been identified as carcinogenic, probably carcinogenic, or possibly carcinogenic to humans. The breakdown is shown in parentheses. The World Health Organization recognized the potential health effects of exposure to static and time-varying electric and magnetic fields need scientific clarification. They explain that electromagnetic fields of all frequencies represent one of the most common and fastest growing environmental influences, about which there is anxiety and speculation. EMF exposure now occurs to varying degrees to all populations of the world, and the levels will continue to increase with advancing technology. Thus, even a small health consequence from EMF exposure could have a major public health impact. As a result, they have information available to the public regarding the current understanding of health effects of EMF and have been sponsoring the International EMF Project since 1996. The objectives of the project are to provide a coordinated international response to concerns about possible health effects of exposure to electromagnetic frequencies, to assess the scientific literature and make a status report on health effects, to identify gaps in knowledge needing further research to make better health risk assessments, to encourage a focused research program in conjunction with funding agencies, incorporate the research results into the WHO's environmental health criteria monographs, where formal health risk assessments will be made on exposure to EMF, to facilitate the development of internationally acceptable standards for EMF exposure, to provide information on the management of EMF protection programs for national and other authorities, including monographs on EMF risk perception, communication, and management, and to provide advice on national authorities, other institutions, the general public, and workers about any hazards resulting from EMF exposure and any needed mitigation measures. The project is overseen by an advisory committee consisting of representatives from 8 international organizations, 8 independent scientific institutions, and more than 50 national governments, providing a global perspective. The scientific work is conducted in collaboration with the ICNIRP. When looking for standards and guidelines related to EMF and Wi-Fi, another reputable source is the IEEE. It is the world's largest technical professional organization dedicated to advancing technology for the benefit of humanity. It has over 396,000 members in more than 160 countries, more than 60% of whom are from the outside the United States. 39 technical societies and 7 technical councils representing the wide range of IEEE technical interests, more than 5 million documents in the IEEE Explorer Digital Library, and more than 15 million downloads from their website each month. They publish approximately 200 transactions, journals, and magazines. It also has an active portfolio of nearly 1,200 standards and more than 900 projects under development, including numerous standards and projects related to EMF and Wi-Fi. Some of their standards are freely available, while others require the payment of a fee. Health Canada also provides information for Canadians regarding EMF and Wi-Fi. To protect the general public, Health Canada maintains its guideline documents, including the limits of human exposure to radio frequency electromagnetic energy in the frequency range from 3 kilohertz to 300 gigahertz, which is commonly referred to as Safety Code 6. This document has been adopted by many organizations across Canada and is referred to in several regulations. Industry Canada has adopted this guideline for the purpose of protecting the general public. As we move into discussing static fields and EMF, it is important to differentiate between a biological effect and a health effect. According to Health Canada, a biological effect occurs when a change can be measured in a biological system after the introduction of some type of stimulus, for example, radio frequency energy. The observation of a biological effect in and of itself does not necessarily suggest the existence of a health effect. A biological effect only becomes a health effect when it causes detectable impairment of health. According to the World Health Organization, health is a state of complete physical, mental, and social well-being, and not merely the absence of disease or infirmity. Some studies may show biological effects without evidence of health effects. This is a consideration when organizations like those previously mentioned are determining exposure limits, along with the robustness and consistency of evidence. Please note that while it is not a direct health effect, pacemakers and implantable cardioverter defibrillators, or ICDs, can be affected by strong electromagnetic fields and radiation. People who have one of these devices should follow medical advice for avoiding situations where EMF is of concern. The intensity and direction of static electric field is stable over time. They are created by static charges or constant DC current. Examples are static electricity on the skin or hair, DC transmission lines, and cathode ray tube TVs and monitors. Household items which produce static electric fields usually produce a field strength on the order of near zero to about 120 volts per meter. Earth's electric field is produced by activities in the Earth's atmosphere. This DC electric field averages about 150 volts per meter near the Earth. Solar activities and atmospheric events, such as thunderstorms, influence the Earth's electromagnetic fields. During a thunderstorm, it can build to several thousand volts per meter. The perception threshold in people depends on various factors and can range between 10 to 45 volts per meter. Static electric fields do not penetrate the body, but can cause a buildup of electric charge on the skin. Health effects of static electric fields are due to the stress of spark discharges. They can also charge particles in the air, which some feel may raise exposures to air pollution, but this is unlikely. A large static buildup, such as would happen in the air during a thunderstorm, brings with it the risk of a lightning or large static discharge shock. This could result in severe burns, cardiac arrest, or death. Static electric fields are easily shielded or grounded. There are no exposure limits per se, but shielding or grounding can minimize exposure to microshocks, which can lower stress. To reduce the risk of a lightning strike or large static electric charge buildup, do not work outdoors if there's a chance of lightning, and do not work in an area with a chance of large static discharge without appropriate grounding or shielding from the field. Static magnetic fields also do not change in intensity or direction over time. You cannot practically shield from magnetic fields. If it is of critical importance, you can shape the magnetic field, but this is expensive. They are created by magnets, moving charges, and changing electric fields. Examples of static magnetic fields include Earth's magnetic field, high DC transmission lines, fast passenger trains, household magnets, MRI equipment, and industrial magnets. Exposure to static magnetic fields will affect electrically charged particles and cells in the blood when moving through the field. The magnetic force can accelerate or reduce the movement of susceptible particles. Only when humans are exposed to strong magnetic fields, such as those generated by MRI equipment or in some specialized research facilities, can we start to perceive the field. Fields of 2 to 3 Tesla or higher can evoke transient sensations such as vertigo and nausea. These result from the generation of small electrical currents in the ear's balance organ. These effects are not adverse health effects in themselves, but they may be annoying and they may impair normal functioning. There is no evidence for adverse effects of exposure to fields up to 8 Tesla, except for limited information on minor effects on hand-eye coordination and visual contrast. The exposure limits for static magnetic fields are different for an occupational setting than for the general public. This is typical of most exposure guidelines. Different devices we use every day operate at different frequencies of the electromagnetic spectrum. We will now go through low frequency and radio frequency EMF in more detail. Low frequency EMF is electromagnetic radiation in the range from 1 Hz to 100 kilohertz. In everyday life, the origin of these fields is mainly related to our use of electric power. AC current is 60 Hz in Canada. Sources include electronic appliances and devices, our power generation and transmission systems, electrified transit, electrical wiring in buildings, and office equipment. Low-frequency EM fields generate electric fields and currents inside the body. These can interfere with the body's own electric fields and current flows related to normal biological functioning. Low-frequency electric fields can also interact with the surface charge on the body. At low levels, all these interactions go mostly unnoticed and do not compromise health. Above a threshold level of exposure, the induced internal fields provoke reversible effects, such as a faint light flickering in the peripheral vision, electric charge buildup on the skin, or a stimulation of nerves and muscles leading to a tingling sensation. These effects occur at different thresholds depending on the frequency of the field. At higher levels, LF causes irreversible cardiovascular effects or tissue burns. Overall research has not shown to date that long-term low-level LF exposure has detrimental effects on health. The basic restrictions for human exposure to time-varying electric and magnetic fields are shown. The F in the internal electric field column is the frequency in hertz. Radio frequency electromagnetic fields are electromagnetic radiation in the frequency range from 100 kilohertz to 300 gigahertz. RF EMF exposure is usually measured in watts per square meter or watts per kilogram. RF EMF are used in radio frequency emitters, such as in magnetic devices for stimulation of bone growth and as part of magnetic resonance imaging systems. For heating purposes, for example, in microwave ovens, and for wireless power transfer in systems such as Qi. They also have industrial uses such as RF heaters, RF sealers, and industrial microwave ovens. Arguably, the most common use of RF EMF is for communication purposes, including mobile phones, base stations, Wi-Fi, 5G, radio, television, and security devices, as they are able to induce an electric current in an antenna. The shorter the wavelength, the more compact the antenna. Communications devices and infrastructure which use RF EMF include towers and antennas, radar systems, pagers, cordless telephones, satellite communications, radio communications, mobile phones and base stations, including 5G technology. After several decades of RF EMF research on numerous potential health effects, the only substantiated effect of RF EMF exposure relevant to human health and safety is heating of exposed tissue. Above a threshold level, which also depends on the duration of the exposure, RF EMF exposure can provoke serious health effects such as heat stroke and tissue damage or burns. Acute or long-term effects of RF EMF exposure below the thermal threshold have been studied extensively without demonstrating adverse health effects. Areas of public and scientific concern are the focus of research. The studies will continue, but if there are any health effects due to chronic low dose, they are likely to be small, as to date they have not been substantiated. The overall evaluation of all the research on RF EMFs leads to the conclusion that RF EMF exposure below the thermal threshold is unlikely to be associated with adverse health effects. The ICNIRP takes into account possible undetected harm by using conservative or reduction factors when developing exposure limits, especially since effects such as cancer take years to develop. The IARC classifies radiofrequency EMF as Class 2B, a possible carcinogen. Included in this classification are household items such as aloe vera, pickled vegetables, and gasoline. The monograph of non-ionizing radiation outlines in detail studies included in the determination of the classification. The ICNIRP guidelines for limiting exposure to electromagnetic fields, 100 kilohertz to 300 gigahertz, is published in the journal Health Physics. It can be found for free on the ICNIRP website. Exposure limits are listed in watts per kilogram or watts per meter squared. Basic restrictions given in the document account for different amounts of time spent in the field. Wi-Fi has become a common technology in modern life that uses non-ionizing electromagnetic waves in the radio frequency band to send signals for the purposes of communication. As such, the health effects will be in line with those just described. In addition to information available from the ICNIRP and the WHO, the ITU and IEEE have standards and information available about these technologies and have set parameters and exposure limits based on the known and possibly undetected health effects. Devices which meet these standards or regulations based on these standards will keep exposures under exposure limits when used as designed and intended. We hope you have enjoyed this overview of electromagnetic fields and Wi-Fi. If you have any further questions about ionizing or non-ionizing radiation, please feel free to contact us toll-free at 1-800-263-5787. 5803 or by email at info@radiationsafety.ca. Visit us on the web at www.radiationsafety.ca or find us on Facebook.